Today, we are embarking on a truly epic journey. We're going to trace a single, profound thread that connects the microscopic, totally invisible world of quantum mechanics all the way up to the massive, macro-level scale of the cosmos. We're looking at multiple bonding patterns, which is basically nature's ultimate strategy for building stability, communication, and real complexity in the universe. Here's our roadmap for today. We'll start with the cosmic metaphor, then dive into the quantum mechanics of overlap, explore the geometric consequences, and finally wrap things up with some incredible astrochemistry applications. All right, let's kick things off with part one, the cosmic metaphor, or thinking of bonding as a language. Before we even think about drawing a single electron, you gotta ask yourself, why do chemical bonds even exist in the first place? To really answer that, we have to rewind all the way back to the Big Bang. See, the early universe was just a hot, undifferentiated plasma, but as it cooled down, gravity started pulling matter together to build stars and planets. Now, down to the microscopic, atomic scale, it was electromagnetic interactions that built complexity. Electrons, whether they were being shared or transferred, became the universe's primary tool for actually creating structure. So think of chemical bonding as a cosmic language. If gravity builds the stars, shared electrons are combining syllables to build molecular complexity. A single bond is like a simple word. A double bond? That's a compound sentence. And a triple bond is just dense, beautiful poetry. Moving right along to part two, quantum mechanics, the how of bonding. Let's actually get into the physical mechanics of how these orbitals connect. It all comes down to the fundamental language of orbital overlap. First up, we have the sigma bond. This happens when two orbitals overlap directly along the internuclear axis, just straight head-on. But nature, it isn't content with just one syllable. Enter the pi bond. This forms when unhybridized p orbitals overlap sideways. Their lobes actually touch above and below that central axis, creating an entirely different physical reality. Now, what's absolutely crucial here is how these two types of bonds behave. Your sigma bond? That's the molecular backbone. Because its electron density is cylindrically symmetric, it allows for completely free rotation. It's flexible. The pi bond, however, completely changes the game. Because it overlaps sideways above and below the axis, rotating the molecule would literally break the bond. It locks the atoms right in place. So while the pi bond is mathematically weaker than the sigma bond, it is vastly more important when we're talking about chemical reactivity and communication.
And that brings us to part three, geometric consequences, the what of bonding.
Let's zoom out just a little bit. We've seen the invisible quantum mechanics, but how does that dictate the actual 3D architecture of a molecule? Well, we can explicitly link the specific type of quantum orbital overlap we just talked about to the resulting physical shapes of the molecules. Literally, the math of the overlap dictates the geometry of the physical world. Let's walk through exactly how this plays out step by step. Step one, a single sigma bond gives you that classic, flexible tetrahedral shape. Think of it as a flexible 3D pivot point. Step two, throw a pi bond into the mix to make a double bond, and boom, that sideways overlap locks the molecule into a rigid, flat, trigonal planar shape. Zero free rotation there. And step three, add a second pi bond to create a triple bond, and the geometry is completely forced into a straight, rigid, linear rod. The shape is entirely dependent on the multiplicity of the bond. And this is a real game changer when we look at nature, especially in organic chemistry. You might be thinking, doesn't the rigidity of a pi bond limit things? Actually, no, it's a feature, not a bug. Take ethylene, for example. It's a plant hormone with a carbon-carbon double bond. That double bond forces it to be totally flat and rigid. Why? Because it has to fit exactly, like a key in a lock, into a receptor protein's binding site to trigger fruit ripening. If it was just a single bond spinning around freely, it wouldn't hold the required shape and the whole biological signal would just fail. Nature literally uses this geometry lock to make biological signaling possible. Which leads us to our final section, part four, interstellar proof, multiple bonds in astrochemistry. Now, to prove that this multiple bonding phenomenon isn't just some local quirk limited to Earth, let's scale things way, way up to the size of the universe. Consider the cosmic presence of two incredibly important molecules, dinitrogen, or N2, and carbon monoxide, CO. You'll find N2 completely dominating the thick atmosphere of Saturn's moon Titan, and you'll find CO drifting through vast, freezing interstellar clouds. And the secret to their survival out there in deep space? They're multiple bonds. Just let this number sink in for a second. 945 kilojoules per mole. That is the bond energy of dinitrogen. Its triple bond, which, remember, is 1 sigma and 2 pi bonds, makes it an absolute atmospheric fortress. It is the strongest bond in any neutral diatomic molecule, and that's exactly why it safely makes up 78% of Earth's atmosphere right now. Standard atmospheric chemistry simply does not have the energy to break that triple bond apart.
But hold on, because it gets even more extreme. 1072 kilojoules per mole. That is the sheer, unadulterated power of the carbon monoxide triple bond. We're talking about the single strongest diatomic bond we know of, and it's exactly this extreme stability that lets carbon monoxide survive the incredibly violent, highly energetic, and just plain extreme conditions of star-forming regions all across our galaxy.
When we take a step back and look at the broader astrochemistry landscape, the true cosmic scale of this is just wild. The chemistry of the universe, from these long linear cyanopol lines stretching across interstellar space to the beautifully complex aromatic rings of fullerenes found in planetary nebula, it's all beautifully, fundamentally built on multiple carbon bonds. The linear nature of that triple bond is literally what makes those giant cosmic chains possible in the first place.
So I want to leave you with a thought-provoking question to chew on. How does the microscopic sideways overlap of completely invisible p orbitals fundamentally shape the macroscopic universe we live in? Think about it. From the ethylene that ripens your fruit to the nitrogen filling your lungs right now to the carbon monoxide drifting between distant stars, it is all dictated by the exact same quantum mechanics. Chemistry really is nature's language.